areas under the curve and total change is what we're going to talk about. You know, all along when we talked about the derivative, we always were thinking of it in the real world. The derivative represents the rate of change of something. What about the area under the curve? It turns out actually the area under the curve also has something to do with change. And the area under the curve of a derivative represents the total change of the function. We're going to try and unpack what I just said in today's lesson. First of all, I want to talk about individual changes versus total change. So I thought, let's look at a bunch of real-world data. I looked up this real-world data. This is stock prices for the Apple Corporation, makers of fine electronics. Their stock price, like every stock price, goes up and down every day, right? And what I did was I looked up for the month of August in the year 2020, I looked up the daily changes in the Apple stock price. Daily changes, right? Some are positive. Those are days when the stock price went up. Some are negative. Those are days when the stock price went down. The daily changes, check it out. I made a chart. These little numbers over here are the daily changes. And if we add those numbers up over the course of the month, for every day there was a change, I'm just going to add together all those changes. Some are positive, some are negative. What you will get if you add them all up is the total net change over the month, right? This is just common sense, right? But another thing you would know from common sense, you could also find the total change for the whole month, not by looking at the individual changes, but the total change for the whole month is just the price at the end of the month minus the price at the beginning of the month. That's another way you could find the total change. So the moral of the story here is the sum of the little changes is equal to the total change. But the total change is also equal to just the final amount minus the initial amount. Or just in the case of this, I'm talking about stock prices, the final price minus the initial price. And you can see on my chart, you add up the total changes. Down there you get this answer. It's like $19 something. But that $19 is the same answer you would get if you took the final price minus the initial price during that month. Now, what's interesting about this thing is not really the intermediate step, but what's interesting for our purposes today, at least, is that these two things will be equal. The sum of the little changes day by day, what they add up to is this number, the final price minus the initial price. Interesting that this sum of little changes involves adding together many things, whereas this is just subtracting just two things, right? All right. Turns out this basic idea, which is pure common sense, is actually related to the meaning of the area under the curve. Check it out. No, why are you up there? If we are looking at a graph of f prime of x, that means that the graph is actually the graph of the changes, not the actual, in the case of the stocks, not the actual price of the stock, but just a graph of how it's changing from moment to moment. Let's say this is going to be over the course of 4 days. Day 0, 1, 2, 3, 4. All right. This is a graph of the derivative of something. This is, of course, the meaning of that in the real world is the instantaneous rate of change. That's what the derivative represents in the real world. How fast the thing is changing at any moment. Can you see on this picture anywhere the daily changes from one day to the next? Well, if I look, say, here, this value tells me f prime of 0. That would be how fast the thing is changing at that moment of 0. f prime of 1 tells me how fast the thing is changing at the moment that day 1 begins, right? Now, throughout the duration of day 1, the rate of change in this case you can see is actually increasing throughout the day, but at the moment that day 1 begins, the rate of change is right there. Let's look at, check it out. I'm going to draw these rectangles. I bet you knew I was going to do that. What do we get if we add these rectangle areas? So they each have delta x of the width being 1. So really they each just, the area here is just equal to whatever that y value is, because the area is always the base times the height, but the bases here are all 1s. So what will we get if we add these areas? It is in fact adding these rectangle areas is pretty close to adding up the daily changes. Like for instance, this rectangle area, how I made this rectangle area is I used the height being f prime of 0. That is how fast the thing is changing at the beginning of day 0. So the area of this rectangle is, if you imagined at the beginning of day 0, the thing was changing a certain amount, and if it just stayed the same throughout the whole day, if it changed the same amount all day long, then the area here would equal the daily change for that day. And then the area here would equal the daily change for the second day, or for day number 1, provided that the change stayed the same throughout the day. This area of this rectangle is the daily change for day 2, with the assumption that the change stayed the same throughout the whole day. Now, of course, the change did not stay the same the whole day, right? You can see the derivative is changing, even in between the days, right? During the days, the derivative is changing. So actually, these 4 rectangles, if I add the areas, it's close to adding the daily changes, but it's actually not exactly accurate, because the change is changing throughout the day, right? If you actually wanted to get a better estimation of the true daily changes, you would make more of these rectangles so that you take into account the changing derivative throughout the duration of each day, all right? If you draw the rectangles with more and more points, you will get closer and closer to adding together the daily changes. And in fact, if you make the rectangles super duper small, then what you get is the area under the curved region, and what you get is the sum of the daily changes. So the actual curved region here, I'm going to have to erase the picture because I'm going to say what I'm going to say. The actual curved area represents, you have to imagine what it is like, is it's as if you were making those rectangles super duper narrow and taking many rectangles. That's how you could get the most accurate measurement of adding up the daily changes. Or the changes, really we don't want the daily changes, we want the changes from moment to moment, because the graph represents the instantaneous rate of change, that is the rate of change at every moment. So the curved area, the true curved area, represents the sum of all the instantaneous changes moment by moment. And what should it add up to? It should add up to the total change. So this area, because it is made up of adding together a bunch of instantaneous changes, this area will equal the total change of f of x. I should have said that before. Right? The curve represents f prime of x. It is the instantaneous rate of change of f of x. If you take the area, you're basically sort of adding up all of those little instantaneous changes, and what you end up with is the total change of f of x. And by total change, of course, I mean the final value minus the initial value over that region on the area. All right? I don't know if this sounds useful, but actually this is super useful. This allows us to make a relationship between the area under the curve of the derivative is equal to the total change of the original function f of x. I'm going to write this using symbols, what I just said. I said the area under the curve of the derivative, that would be something like this. Remember this integral sign with the letters? That's the definite integral, and this means the area under the curve of f prime of x from x equal a to x equal b equals the total change of f of x from x equal a to x equal b. And what is that? I keep on saying it's the final value minus the initial value, but actually you can write that in very simple terms. It's this, f of b minus f of a, right? This is what I mean by the final value. The value at the end minus the value at the beginning. Okay? This here has a name in our book. This is called the Total Change Theorem. All right? This is the relationship between the definite integral and something about change in the real world. It says the definite integral of the derivative equals the total change of the original function. This is quite useful in the real world. Let's try an example. All right, in this problem, P of t is the population of my town, say. I just made this up. T is measured in years. And here you see a graph of P prime of t. That is how fast the population is changing over time. So right at the beginning, it starts at 0. That means at time 0, the beginning of year 0, population is not changing. By the first day of year 1, you see the population is increasing 100 people per year, right? All the units of t are in years here. At year 2, the increase has stopped and it's at 0 again. At year 3, now the population is decreasing at a rate of 200 people per year at the beginning of year 3, and so on. That's what this graph means. Your job is to estimate the total change in the population from time 0 to time 6 using rectangles on the right endpoints and using n equals 6. Why did I say all this about rectangles? Because as we know, what I just wrote, the total change theorem, it says that the total change is equal to the definite integral, that is the area under the curve. And so if you want to estimate the total change, that's the same as estimating the area under the curve. And for that, you need to use the rectangles or the trapezoid or the Simpsons, right? Those are the methods that we've talked about for estimating the total change. Now, I didn't give you a formula for any of these functions. I just drew the graph for you. Can you do this without using a formula? Yeah, just at the step in which you would have plugged the number into a formula. Instead, you look on the graph and find the value that way. All right, let's do it. I'll do it down here. I gotta erase the question. Hope you wrote it down. Anyway, because of the total change theorem, really what we're trying to do is this definite integral. The integral from 0 to 6, that is the area under the curve, from 0 up to 6, of p prime. It's this function, which is the derivative of something, which is what we want to find. Okay, this, in our approximation, will be estimated by doing the rectangles thing. So the way that I would do the rectangles thing is draw a little chart of the interval that we are considering. It goes 0 to 6. And I said n equals 6. You got to divide this into 6 pieces, which works out nicely. You can just go 1, 2, 3, 4, 5, 6, right? The delta x then, you can tell by looking at my chart, the delta x is 1. So I hope you remember the formula for the rectangles. I said using the right endpoints. That means I'm going to pick these guys, 1, 2, 3, 4, 5, and 6. And so the formula, it has delta x on the outside, which in our case is just 1, times, I'm going to plug all these values into the function, and the function in this example is this, p prime of t. So I begin with p prime of 1 plus p prime of 2 plus etc., ending up with p prime of 6. I said p prime because the total change is equal to the area under the curve of the derivative. So p prime goes there. How do you actually find these? In all of the examples we've done in the past, you were just plugging into some formula. We don't have a formula, but we have the graph, so we can plug in by looking at the values on the graph. What is p prime of 1? This is a graph of p prime. When I use t equals 1, I get 100. So that is 100. Plus, I don't need this parentheses, do I? This is a 1 on the outside. That won't do anything. All right, what is p prime of 2? I look on the graph right here, 0. P prime of 3, I look on the graph here, and it's negative 200. P prime of 4, I look on the graph here, and it's also negative 200. P prime of 5 is here, which is 0. And p prime of 6 is here, which I'll say is 100. And we add these up. What do we get? 100, minus 400. I get positive 200 and minus 400. This is minus 200. So what's my conclusion in the language of this problem? My interpretation here is that during this time, from time t equals 0 to t equals 6, the population of the town decreased by about 200 peeps. All right, I say about because this is just an estimation using the rectangles. All right, how would you find the actual total change? Well, the actual total change would be whatever these areas are, the true areas. The true areas would be impossible to figure out in this example because I didn't tell you a formula. You have no way of knowing what those areas are. So this is an estimation though. These areas, if you count this one as negative and this one and this piece as positive, they should add to about negative 200. Let's just try a more accurate answer would be if we use the trapezoid or the Simpson's rule. Let's try the same thing using Simpson's rule. More accurate if you use Simpson's rule. Do you remember Simpson's rule? I'll refresh your memory of the formula. This is the formula for Simpson's rule. You got b minus a over 3n out front, and then you add together all the points. You have no coefficient on the first and the last point, and the other ones alternate 4s and 2, 4 then 2. All right? This is the Simpson's rule. I think we can just immediately plug everything in. And remember, b and a are the two endpoints. So on the outside, I'm going to get 6 minus 0 divided by 3 times n, which is 6. And then in here, we add all the values up here. Now, this f is going to be p prime. So I'll write out p prime of 0 plus 4, p prime of 1 plus 2, p prime of 2 plus 4, p prime of 3 plus 2, p prime of 4 plus 4, p prime of 5 plus p prime of 6, right? Those are all the points with the appropriate coefficients in front of them. And these, again, we find those values by just looking at the values on the graph. What do we get? Can I fit it in down here? I'm going to try. 6 over 18, I guess. And then p prime of 0 is 0 plus 4 times p prime of 1 is 100 plus 2 p prime of 2, which is here, 0. Plus 4 p prime of 3, which is down here, negative 200. Plus 2 p prime of 4, which is also negative 200. Plus 4 p prime of 5, that's 0. 4 times 0. Plus p prime of 6 is here, 100. And this, you can just add that all up and put it in your calculator. I think I'm totally out of room. When I plugged this into my calculator, I got negative 233.3 repeating. All right, so this, we have no real way of knowing the true figure here because you don't know any formulas for anything, but this is likely to be a better estimation than the one I did before with the rectangles. And so my final answer here, we don't need the picture anymore. From year 0 to year 6, the town lost about 233 people. They bailed.